transformations starting this today. We'll do as much of this as feel like we have time for, and then we'll switch over to eigenvalues and eigenvectors, which we have talked about some already after we talked about determinants. So we'll talk a little bit more about that, and in particular, a specific reason why we do eigenvalues and eigenvectors. So that's where we're headed for the rest of the semester. I believe our final exam, I don't know if it's official yet for final exam schedule, but I believe ours is scheduled for 8 in the morning on the Wednesday of finals week. I didn't take that. Don't shoot the messenger. So if you would like to take it at a different time prior to 8 a.m. on that Wednesday, I'm open to having you come in at a different time and take it, just like we've done the other exams. The only thing that I ask is that we need to start it by 8 a.m. on that Friday, Wednesday. But if you want to do it on Tuesday afternoon rather than Wednesday morning, that's perfectly fine with me. Just to give you an option if you don't want to have to be up at 8 a.m. to take final. So, all right. Anyway, let's talk about linear transformations. So, this first part just starts talking about what we mean by a definition of a linear transformation. So remember the notation that we have there, the T notation with the colon and the arrow. We're just using that as our function notation. So a linear transformation to start off with is just a function. The domain and codomain are both vector spaces. What we mean by a linear transformation is that something, basically the function behaves like you would wish all functions behaved, if you will. So there's two properties that you need to show that something is a linear transformation. The first one is that, I'll call it u plus v. If I do the transformation of a sum of two vectors, what would you like to have happen? Yeah, you'd like it to break up over the sum, right? It's a v. The other thing is that if I have a constant times a vector, what would you like to do with the constant? Break it out, yeah. So those are kind of the two nice properties that you would like to have most functions have, right? You'd love it if a function distributed over a sum. You'd love it if I have a constant on the inside of the function. I have two sets of equal signs in there. And you would love it if they have a constant on the inside of the function. You could pull it on the outside of the function. And that's exactly what a linear transformation does. So, linear transformations have lots of different uses. Again, we don't have a lot of time to get into a lot of application things, but anytime you want to change something, maybe morph something on a computer screen, for example, that might be an example of a linear transformation, or maybe something that's an affine transformation where we have to shift it and then move it around. So if you've got things that maybe stretch or shrink or shear, those kinds of things would be linear transformations. So for example, what I mean by a shear is maybe you start with a rectangle and push the top and turn it to a parallelogram. That's a shear. Yeah. So those kinds of things are linear transformations. I have to be a little bit careful because we might want to think about shifting things around. That's not quite a linear transformation, but sometimes that's an affine transformation. And affine just means you moved your origin somewhere else, and then maybe did a linear transformation. So anyway, linear transformations satisfy those two properties. So this next part here is just some examples of different things to show that they are linear transformations. If you want to show that something is a linear transformation, you need to show that it indeed will break up over a sum or break up, pardon me, or the constant will pull out. You need to show both of those properties. So this first one, we're taking a vector in R3, mapping it to another vector in R3 according to that transformation. So if we wanted to brute force check that this really is a linear transformation, take two vectors in R3, add them, apply the transformation, or apply the transformation then add and see if you get the same thing. So this would say apply the linear transformation to the vector, I won't put the extra set of parentheses in here now, x1 plus x2, y1 plus y2, z1 plus z2. This one, when we do the output, we'll put the x1 plus x2 in where we see the x, the y1 plus y2 where we see the y, the z1 plus z2 where we see the z, and I've got to do it in all three components, so I've left myself not enough room. I'm good at that. It should be a plus, thanks. There's a plus sign, yeah. So I'm just plugging in the x1 plus x2 in for the x, the y1 plus y2 in for the y, the z1 plus z2 in for the z. I need to show that this does break up. So I could either plug in, do the t of x1, y1, z1, and the t of x2, y2, z2, and apply the transformations and see if we get the same thing. Or I could just break this apart. Let's just play with this particular vector. What can we do with the constants there in front of the sum? Distribute, and then I've got a sum of things again, right? So I can just split it into two pieces. So this really will equal 7x1 plus 2y1 minus 8z1, comma, negative y1 plus 5z1 and a 4x1 plus 7y1 minus z1. That's a comma there. And then plus the same exact thing, but with 2's rather than 1's as subscripts. And that really is the transformation applied to x1, y1, z1, plus the transformation of x2, y2, z2. So we really do get where it breaks up over the sum. The other two won't be as horribly horrible notation. To show that the constant pulls out, we can do that really quickly. Notice that if I have, try to do this off to the side over here. If I have the transformation of c times x1, y1, z1, the first thing that we can do is distribute the c to each of the components, right? When we do that, notice that we're going to have a c absolutely everywhere in here, aren't we? You'll have a cx1, a cy1, a czz1, cy1, czz1, cy1, or x1, y1, z1 again, right? What can you do with that c after you do that? Pull it all the way out in front, right? So 7c, c, x1, 2c, y1, 8z, cz1, minus cy1 plus 5cz1, 4cx1, 7cy1. If I could remember to write the constant. And then, like we said, there's a constant in absolutely everything. so I can factor it out or pull it out. Since there's a constant absolutely everywhere, I guess technically I'm doing that in 2 steps, right? I'm pulling out the C out of that sum, pulling the C out of that sum, pulling the C out of that sum, and then pulling the C all the way out in front of the vector, right? Recognizing it as a scalar multiplication. And then finally, that's exactly how our transformation is defined. Where did I put that? That was ugly and not fun. Straightforward, but ugly and not fun. At least I think it was ugly and not fun. Maybe there was an easier way to do that. I bet you there was an easier way to do that. Okay? All right. Let's look at the individual terms here. Notice that this part right here, if I think of this as a dot product of vectors, this first one would have been 7, 2, -8, dotted with x, y, z, right? Notice it's the same format here, except my vector would have been 0, -1, 5, dotted with x, y, z. Right? Yeah. Okay. The last one, what would have been dotted together there? 4, 7, -1, and then dotted with x, y, z. Good. So notice that this first vector, this second vector, this third vector, the left vectors, if you will, are all dotted by the exact same thing. I'm just changing it as I go component to component, right? Notice if I think of this x, y, z as a column, then that would be exactly row times column for first row times column for second row times column for the third row, correct? I could have written this transformation as the matrix 7, 2, -8, 0, -1, 5, 4, 7, -1 times x, y, z this way. Could do it as matrix multiplication, right? Because I would get the, I'm writing it vertically rather than horizontally, but that doesn't matter as far as where I'm talking about the vectors. But this is a little bit easier, a little bit straightforward, more straightforward, hopefully, to figure out why this had to be a linear transformation. If I do a sum of 2 inputs here, I've got matrix multiplication. We already know that matrix multiplication distributes over sums, right? Right? And if I have a constant times this vector here, I know that I can pull the constant out in front because we've already proved that for matrices, right? So if you have a linear transformation that goes from Rn to Rm, is defined by T of x equals A times x, where A is an M by N matrix. Then T is a linear transformation. So matrix multiplication by a vector is a linear transformation. In fact, when we have a linear transformation defined this way, we actually write it as T sub A this way. And put a little subscript on the T. The T sub A refers to the fact that we're defining this linear transformation as matrix multiplication. And again, if I had it defined as matrix multiplication to start with, then again, the process of showing that this really is a linear transformation would have been a lot shorter, especially from a notation standpoint, right? We agree? Because if you had t sub a of x plus y, that certainly is t sub a of x, or time, sorry, this is a times x plus y, which is ax plus ay, which is t sub a of x plus t sub a of y. That was a lot shorter proof, wasn't it? When I had it written as a matrix multiplication. Right? And didn't have to go through all those subscripts. Okay. And I could do the same thing for constant multiples. Same type of proof. All right. Questions on that example? Notice one thing I will notice as well. Notice I wrote this as R sub n to R sub m, and my A had to be an m by n matrix. Okay. Notice it looks like it's flipped around. Okay. All right. Let's do the next one. The next ones don't require so much notation. This one says, take a fixed vector in Rn and define a linear transformation as the transformation on the input is just dot it with y. The y doesn't change. The x can. The x is the input, but the y is fixed. Okay? So again, if I've got two vectors here, the definition says I'm going to do x1 plus x2 dotted with y. What do you think we should do next? Split it up, right? Yep, x1 dotted with y, x2 dotted with y. And that's exactly how the transformation is defined. So notice that the reason why this first property is true is because we know that inner products, dot products distribute over sums. Doing the second property to show that the scalar can get pulled out. Well, here is the transformation applied to a constant times x1 dotted with y. But what can we do with this constant? Take it out of the dot product. And get the constant times the transformation. That one okay? Yeah. Okay. This last one, without having to go through all the details, why is that going to be a linear transformation? What do you know about integrals? You split them up over sums and take constants out, right? So integration here on that function space will give us a transformation from that function space to the real numbers. And it'll work because, again, integration breaks up over sums and integration constants will pull out of the definite integral. Without going through the details, we already know that one. All right. So this is how you would check that something is a linear transformation. This one asks if things are or not. This one, we have a function defined from an inner product space to the reals, where the transformation, the function applied to the vector is the magnitude of the vector. Is that going to be a linear transformation? Do magnitudes, do norms break up over sums? Remember, if it's going to break up over sums, if I had the norm of u plus v, what would that have to equal? If it's going to break up over sums, literally with the notation, what would it have to equal? Good, yep. Norm of u plus norm of v, good, right. Is that always true? No. In fact, the theorem, what does the theorem say about this symbol right here? What is this? Not equality, but there's a named theorem.
This is the greater than.
What is this symbol instead? It's less than or equal to, right? What do we call that inequality? Cauchy-Schwarz is this one. But this is a consequence of Cauchy-Schwarz. Triangle inequality, right? That's triangle inequality. Good. Okay, so again, if you think about how you would write these two vectors, if you had u and v, then your sum goes that way, right? So this is triangle inequality. All right, so it's not equal to, it's less than or equal to. Do you anticipate this being a linear transformation then? No. Okay. So let's find a specific example where it's not. Let's let our vector space be R2. Let's say our U is the vector 1, 0, and V is the vector 0, 1. Let's take a specific counterexample here. Let's do the second part first. The transformation is take the magnitude of the vector. What's the magnitude of U? It's magnitude of V. 1. So this is going to equal 2. The next one says add them together first and then take the magnitude. What do you get for the magnitude of the vector 1, 1? Square root of 2, right? And these two are not equal to each other. So this is not a linear transformation. Same idea here. Do determinants break up over sums? Or said another way, do scalars just pull directly out of determinants? No. No. So this is, would we anticipate this being a linear transformation from the set of matrices to R? No. Again, let's pick a specific example. Okay. Let's take A be the matrix 1, 0, 0, 0. Let's take B to be the matrix 0, 0, 0, 1. What's the determinant of each of those two matrices? 0. But if I add them together, what matrix do I get? The identity, which has determinant 1. Yeah. So again, not a linear transformation. Both of these are familiar functions, right? Both of these are things that we've taken functions on vector spaces before. Well, I guess the first one's technically an inner product space as well, but taking a norm is a normal thing to do with regard to vectors, right? But that's not a linear transformation. Okay. Taking determinants of matrices is another normal thing to do, but that's not a linear transformation. They're certainly functions, but they're not linear transformations. Perfect. Let's look at the next one. Again, if it's going to be a linear transformation, it needs to break up over sums and pull out constants pull out. Do transposes break up over sums? I believe they do, don't they? Yeah, that's one of our theorems. Isn't it going to do constants pull out? Yeah. Yeah. So this one will be a linear transformation. If I do T of A plus B, that's A plus B transpose. The transpose breaks up over the sum, so you get A transpose plus B transpose. That is the transformation on both of those matrices. Likewise, if I take the transformation of C times that, that's C times A transpose. C times A transpose, which is C times the transformation A. So this one is a linear transformation. So transpose works. This last one says doing the transformation on polynomial space, degree 3 or less. And it just says take the polynomial and add 1 to it. Is that going to work? No, this one's not going to work because if I add them together first and then apply the transformation, what's going to be on the end? Plus 1. If I take the transformation of them, both of them first, and then add it together, what's going to be on the end? 2, right? So if you have T of P of X plus Q of X on the inside, we get P of X plus Q of X plus 1, but T of P of X plus T of Q of X is P of X plus 1 plus Q of X plus 1. And they're not equal to each other. Does that make sense? This would be an example of one of those things I mentioned before. This is called an affine transformation. It does a shift as well. Okay. If not for the shift, it would be a linear transformation. It would work just fine. Okay. All right. Questions on any of those examples at all? All right. We already talked a little bit about this one. We're going to do the matrix of the linear transformation. Again, we're looking for row dotted with column, right? And making a matrix out of that, okay? Notice that our input here is a 2-dimensional vector. Our output is a 3-dimensional vector, right? So our matrix A that we talked about a little bit ago, if we're going, this says that we're going to go from R2 to R3, right? Input is 2-dimensional, output is 3-dimensional. If we go from R2 to R3, then our matrix, I'll just refer to it as A. Our matrix A is what size? 3 by 2, right? It flips it around. Because again, remember, if our input is a 2-dimensional vector, that's the thing that's going to go on the right-hand side of the matrix, right? So if it has 2 rows, I need the matrix to have 2 columns. The output needs to be a 3-dimensional vector, so I need to make sure I have a dimension 3 for my number of rows here, right? So again, if I want to write this as matrix multiplication, I need some matrix. We said it was going to be 3 by 2. Our input is a 2-dimensional vector. And our output will be some 3-dimensional vector. So I'm just writing it this way just to illustrate what's going on. Again, think of these as inner products. Think of these as dot products. What would I need a dot with xy to get negative 2y? What does the first row need to be? Okay, no x and negative 2y. 0, negative 2, right? what would the second row have to be then if I'm going to get 3x when I'm done? 3, 0, good. And the last one, if I'm going to get x minus 2y, 1, negative 2, good. And then you can see that if you multiply those together, you really do get what we're supposed to, correct? So again, this is the matrix of our transformation, this matrix here. So our A would be 0, negative 2, 3, 0, 1, negative 2. So far, so good? Look at the next one. Dimension of our input space is, dimension of our domain is 4, good. Dimension of the codomain, dimension of the output space is 3. I've got 3 components, right? See the comma separating them there? So this is going to go R4 to R3. So our matrix will have what size? 3 by 4, good. So we should be able to identify the rows pretty quickly now as we go across. What's the first row going to be? Good, yeah. 7, 2, negative 1, 1 is just the coefficients on those. X1, X2, X3, X4. Second row. Good. Last row. Yeah, negative 1 and then a bunch of zeros. Good. Pulling those straight out. Yeah? Okay. All right. So these last ones are talking about some geometric things. We've got projection and we've got reflection. Both of those turn out to be linear transformations. So the goal of this is to figure out a matrix for these transformations. So the first one says projection onto the y-axis. All right, so what does that mean? Let's think about it geometrically. That is not projection onto the y-axis. That's not the right directions. Projection onto the y-axis would be changing everything into R1, not R. So let's cross that out. And let's say projection onto the XY plane. That's what I really mean. Cross that out. Projection onto the y-axis. If we're going to be on the y-axis, that would mean your x and your z had to be both 0. That's a different projection. You can do it. It's just that's not what I wanted this problem to be. All right. So I've got some point up here at x, y, z. Projection onto the xy plane means we're going to come down perpendicularly to the xy plane. What would the coordinates of that? If we're going to drop down perpendicularly onto the xy plane, what would the coordinates of that point be? X, Y, 0. Good, yep. So this would mean that your transformation would be x, y, 0. That's what it says to do, right? Project onto the xy plane means drop it straight down. Can we figure out what the matrix is here? What size will it have, start with? So this one, notice I got it written differently. So notice that this says we're going from R3 to R2, right? I've got it written right now as R3 to R3, right? So if I really wanted to go from R3 to R2, what would I do with the last component? You know, just take it out, right? If I want to go from R3 to R2, I just take out the last component, wouldn't I? So what we're saying here is that we can really treat the XY plane like it's just R2. Okay. All right, so this will be a 2 by 3 matrix. What will be your first row? Be 1. So looking at this component here, how many x's do you have? How many y's do you have? And how many z's do you have? 0, right? So it'll be 1, 0, 0. And what would the second row be? That was really weird. Oh, there is a y. Yeah, no, we're looking at this part here. Yeah, the second row. What would the second row be? 0, 1, 0. That's where the y is going to come in. If we were doing this from R3 to R3, what was your last, looking at it from the first part here, what would your last row be if we were going from R3 to R3? All zeros, yeah, it'd be 0, 0, 0 there. Good. All right. We want to reflect around the line y equals negative x and figure out what the matrix would be. So if we have the point x, y, and I want to reflect around the line y equals negative x, where would you end up? Yeah, it flips them and negates them, right? Yep. Just notice if you were over here, you'd end up over there. Okay. All right. Does it negate them? That one would be negative. Got to be a little bit careful with the. Well, I'm worried about this one up here. So if I was here and here, so it's not negative y negative x up there, is it? Certainly if we did the other one, if you did y equals x, you know that one. Because if this is xy here, this one's going to be, that one's yx, right? So you should be able to do that one. All right, so this is just in interest of time. Think about that one for next time, about what the coordinates would be so we can get the matrix. So think about that one for next time, just for interest of time. All right. So I want to finish off at least a little bit of this stuff before we end for today. I got about 8 minutes, and I want to make sure I talk about this because this part's pretty important. So we want to see how linear transformations behave in terms of a basis. Well, again, the whole point of having a basis is that we can write everything in my vector space as a linear combination of the basis vectors, right? So if I have a basis for v there, how can I write x for sure? If I know that the v sub i's here form a basis, then how can I write x? Yeah, the linear combination of the basis vectors, right? Agree with that? So if I want to apply the linear transformation to x, that means we're going to apply the linear transformation to the linear combination. It's a lot of linears. But what can I do in regard to the linear transformation? What can I do first? I can just break it up over the sum, and then what can you do with each of the constants? Pull them out in front, right? So I can rewrite this as C1 times T of V1, C2 times T of V2, Cn times T of Vn. And what does that tell us? What it tells us is that if I know what the transformation does to the basis vectors, then I know what the transformation does. Say it again. I know what the transformation does to the basis vectors. I know what the transformation does. That's what that says, right? Because I can figure out what the output is for any vector in terms of the outputs of the basis vectors. So that might be something to help out with figuring out that one I said to think about for next time. If you can figure out what are the basis vectors for R2 that you would probably use here. Yeah, 1, 0, and 0, 1, right? Figure out where 1, 0, and 0, 1 go. If you know where they go, then you know where everything goes. That's what this says. Okay. So think about it, see if we can apply that up there. In any event, let's see if we can do this problem. We have vectors v1 and v2, negative 2, 1, and 1, 3. We know what the transformation does to v1 and v2. It asks us to find a general rule. That's what the t of xy says to start with, is find a general rule, and then find what the output is specifically for t of negative 2, 3. Okay. How might we figure out a general rule for this? So put what in a matrix? Well, those are the outputs, though, so I don't want to put those in a matrix. Yeah.
A times V1 equals negative 1, 0, 0, 2, 0, 2, 0, 0, 10, and A times 1, 3.
So you're saying that if I have what size? Well, okay. So what size matrix would I need to start with? Let's go there. Okay. And why is it 3 by 2? Good. The inputs are R2, the outputs are R3, so you need a 3 by 2 to start with, right? So you're telling me that if I did A times negative 2, 1, I should get negative 1, 2, 0 like that. We should write it the other way. This way. Know what you were saying? And then A times 1, 3. And go B. I should write them vertically since I'm writing matrices here. But I didn't write it that way. You're trying to figure out what A is from there? Seems like a lot of equations to try to solve. Because I got 6 entries you have to figure out, right? It's a good thought. We definitely have to have those, but I don't know what A is, And I definitely know it's not invertible because it's not square. So I don't have a lot of help in that regard. But I definitely would have 6 entries I have to figure out at that point, right? So it's going to be a 3x2. Let me ask you this instead. What if I didn't ask you this part? I asked you this part to start with. How could you use what we talked about first? Or just not first, but just a minute ago above. How can we use what we talked about above to help us with that? What did the previous thing above say? Yeah, go ahead.
Find 2, -3 relative as a combination of V1 and V2, and then use it or use the same combination of the transformations to find it.
Yeah, good. We can figure out what the coordinates are for this 2, -3 in terms of the basis we're given, right? Right? So I want to solve that. Oh, let's see, I don't have my calculator on me, and I'm out of time anyway. But let's see. Two, 7. All right. 2 times that, 2 times that, 7, 2 times. Whew, I didn't make never have very many friends there with that number. So I would have what? -4/7 for the second one. Boy, that was not very nice of me to do it that way. -4/7, -12, +12/7. That's -21/7. So -9/7. If I did my arithmetic right. So your t of -2,3 should be -9/7 times t of v1 minus 4/7 times t of v2, and now you should be able to finish it off. Assuming I did my arithmetic correctly. I'm not going to make any guarantees with that. Did I mess up?
No, never mind.
Okay. I'm not going to make any guarantees I did my arithmetic correctly here. But notice that you can find the coordinates of 2, -3 relative to the basis you're given, the -2, 1, the 1, 3, right? We've done that kind of problem, haven't we? And we use the coordinates to use that to multiply by the outputs of the basis vectors, and that'll give us the transformation. So if you wanted to find a general rule, you would do the same kind of thing, except that here you would have an x1. We'll do it the same kind of way. All right. Anyway, pardon me. We'll talk more about this next time. And we'll also get into kernel and range. I thought I might get there today, but didn't get